Okay. All right, let's get started. I know I said I was going to try and get your exam done by today. It just didn't happen. I really tried, but it's been a little hectic. So I think 6.2 has been graded. If not, I'll check, but I think it's been graded. 6.4 and 6.7 I know are still being graded. How did the first influence line assignment go? Is that not too bad? Okay, good. I do want to make sure that we've got our eye on the big picture, so I did want to make 2 points. I did place a little PDF. If you go to the analysis project section on Blackboard, there's a little PDF for installing AutoCAD if you have not yet done so on your personal machine. And there is a little a note on there that you can download it for Macs as well. I could have sworn there was an option for Civil 3D for Macs, and there's not, so I found that out recently. So I'm working on a solution for that for those of you that are in CE 241. But we are figuring that out. But I did want to make a note for those of you that are deciding to engage in more horrendous torture with me by taking steel design next semester. Is there anybody planning on taking it in here? Okay, a few of you. All right. I do want to mention a note about this. This is the steel manual. You've probably heard of it from friends, right? So I do want to mention a note. Come on in.
Hey, everybody.
It's class begins at 11. This is going to make fun recording. So okay, let's talk about the manual. So when you register for CE 414, the class is listed with no textbook, and that is correct. There is no textbook for steel design. I make all the problems myself. The specification you can get for free and all that. So I don't need a textbook for the class, but you do need a manual. Okay, you really can't do steel design without the manual. In fact, when you take the FE exam, there are snippets of the manual inside the reference manual because again, you can't really do it without it. If you were to try and buy this off the shelf right now, just as a private individual, it'd be like $400. I'm not making you all spend that much money, that's for sure. We have a manual discount program that takes this and drops it to like $125. It's a lot cheaper. What happens is I request a coupon code through AISC, and then what happens is once I get that, I email that out to the students that are registered for the class. So if you're thinking about taking steel design, try and get registered for it somewhat soon. I'm not saying you can't, you don't have to register for it today, but if you can get it registered for it within the next couple weeks, that would be good. Usually, I've already made my request from AISC for the code. It should take a few weeks for the code to be issued, and then I will distribute that. The way I have steel design structured, you don't need the manual for the first week. But after the first week, we'll be bringing it to class like every day. So you'll want to try and get your manual as soon as possible. And it's got to be the gold one. So you might have friends that have a blue one, but it's got to be a gold one. If you're working at a firm or a company that has a gold manual and you want to borrow that, that's fine too. But it's got to be gold. Any questions? Okay. All right. So we are going to continue our discussion today on influence lines, and what we're going to be looking at is influence lines for shears and moments. Okay, let's just sort of recap what I think is probably the most important takeaway from the previous lecture, which is the Muller-Breslau principle. So if you recall, the Muller-Breslau principle is the tool that we use to graphically construct shear and moment influence lines, or not shear and moment influence lines, just influence lines in general. And if you read the principle just verbatim, it says that the deflected shape of a structure represents to some scale the influence line for a force effect if the quantity in question is moved through a small unit displacement. So what that means is we have to identify a response of interest. So are we drawing an influence line for a reaction, which is what we did last time. So last time our goal was to draw the influence lines for all the support reactions. So for each influence line, we would identify that support reaction. We would remove from the structure the ability to resist that response. So in the case of a support reaction, like if it was a roller, we would just get rid of the roller. And then we would move the structure through a unit deformation. And then whatever the structure looked like after it was deformed, that was the influence line. And we ended up getting diagrams that looked like this. We were able also to develop some general guidance and rules for drawing support reactions influence lines. So for example, when we're drawing the influence lines for reactions, if we did all of them, like we in the case of what's here on the slide, we know that the influence line is for a given reaction is going to equal 1 at that reaction and then 0 everywhere else. We also know that if we're dealing with statically determinate structures, influence lines are lines, okay? No curves, no anything like that, okay? And then the third thing is that in the hinges serve to change the direction. But then there is actually a fourth rule, which I don't have drawn here on the screen, which is that if you're looking at just the reactions, that plus that plus that is 1. That plus that plus that is 1. That plus that plus that is 1. That vertically, if you sum all those values, that equals 1. That is not going to be the case for shear and moment influence lines, so there's sort of a reason I'm not really highlighting that, but just for influence lines for reactions, that observation holds true. Okay? Does that make sense? Okay, so now what we're going to do is we're going to draw or use the Muller-Breslau principle to draw influence lines for shears and moments. Now, the same principle holds true. We have to pick a spot of interest. Okay? So if you're ever looking at either problems in the textbook or problems that I'm doing here or just problems in general, you will tend to find that point of interest identified one of two ways. So you might have, let's say here's a beam, and here's a beam, and we have a support here, we have a support here. We'll call this support A and call this support B. And so if we're interested in this point right here, we might call it, I don't know, point C. But what I think is probably more common is to actually just draw a section line. So we'll call this like section 1-1, and we'll say, bless you, draw the influence lines for the shears and moments at that section. So you'll probably see both references in the textbook, or you know, if you're ever just looking at calcs as an engineer, but you'll see one or both of these. Okay, and so what we do is we pick a spot of interest and we follow the influence line by, we do the same thing, we remove from the structure the ability to resist the response and we move it through a unit displacement. For shears, it looks like this. For moments, it looks like this. Okay, the only drawback to, and I'm going to talk to you about how I get these here in a bit, so I'll just tell you, like, this is what the shear influence line looks like, this is what the moment influence line looks like. Right now, I'm just kind of giving you a picture as to what they look like. I'll tell you a little later about how we actually quantify that. Now, one of the drawbacks of influence lines in general is that you can only draw shear and moment influence lines for a given point. So the question is, how many points is enough? So for example, if I'm trying to fully define the moment effects on this beam, how many cuts do I need to do? Do I do 5 of them? Do I do 100 of them? Like, how many different times do I need to cut this thing and draw an influence line until I accurately capture the shears and moments on that beam as a load is moving? Common practice in bridge engineering is to draw an influence line at every 10th point. Okay? So if you have a bridge that's, let's say, 50 foot long, then you'll draw an influence line at x equals 5 feet, x equals 10 feet, x equals 15, x equals 20, at every 10th point. And then you're probably a little fuzzy right now on what I mean by the shears and moments. And if I were to throw the term shear and moment envelope at you, you'd probably be like, I don't really know what he's talking about there. Don't worry, we'll cover that probably sometime next week when we get into envelopes and applications and whatnot. But in the land of bridge engineering, 10th points is really what we're after. Now, before we review like how to actually draw these influence lines, I do want to go through some sign conventions here. Whenever you're looking at influence lines, the sign convention follows the inside response, the internal response. For example, we're looking at the shears and moments inside the beam, you know, at a particular point. So for positive internal shears, the sign convention looks like this. Remember, if we cut a section and we look to the left, we say that downward shears are positive. If we cut a section and look to the right, we say positive shears are upward. So if I go back here, so if you look at this influence line, the left, so here's where I cut the section, the left side goes down, the right side goes up. That matches this right here. Okay, so that's why we're drawing it in that fashion. Okay, so these are positive internal shears. Positive internal moments look like this. So both moments tend to rotate the section up like this. Okay, so before we get into how we actually draw the influence lines. I just want to make sure that we're all clear on the sign convention. Does that make sense? Everybody good with that? Okay. All right. So let's start off with shear influence lines. So I'm going to go through the rules for drawing shear influence lines first. So I have a beam here, and I'm cutting a section right here, and so I'm trying to be a bit general with my notation. So we're going to say that the beam, that this distance is L1 and this distance is L2. Okay? So what we're going to do is we've identified the points. Let's go through the 3 steps. Okay? So step 1, if I want to draw a shear influence line, is I have to pick a point of interest. In this case, I picked this point, which I'm calling section 1, and it's some distance L1 from the left support and some distance L2 from the right support. Okay? And so what we do is we install at point 1 what we call a shear release. And basically what we're doing is we're removing from the structure the ability to resist shear at that point. Now this is what's called a shear release. We've never really dealt with a shear release in this class up until now, and this will be the first and last time that we deal with it. But we have dealt with releases before. Does anybody have another name for a moment release? A hinge, right? So a hinge is a point on a structure that does not have the ability to resist moment, okay? I am saying that this is a point on a structure that does not have the ability to resist shear, okay? All right? Now, what we do is we take that and we move it through a unit displacement. Now, the way that that works is that in order to move it through a displacement, okay, so for example, let's say here's my shear release right here, so we'll just sort of draw it like this. Okay, I have to move it through a unit displacement, but I'm only trying to displace it from a shear standpoint. So what that means is that we've got to displace it such that this side goes down and this side goes up. Okay, so we're putting the left side down and the right side up, and we're doing that because that follows our sign convention. Okay, so this is going to be what our displaced shape looks like at the end. Okay, now we're moving it through a total unit displacement. So this entire distance is 1, okay? So that's the total displacement, okay? So if you look here on the slide, what I've got is I put some notation here. I'm going to call this H1 for this side and H2 for this side. So that total height equals 1, okay? But what makes shear influence lines a little unique, because we're releasing shear and we're not releasing moment, what that means graphically is that these 2 lines have the same slope, okay? So the idea is that if I look at this line, the slope is H1 over L1, and I look at this line right here, and this slope is H2 over L2. The idea is that I have 2 equations I can solve. I have H1 over L1 equals H2 over L2, and my second equation is that H1 plus H2 is 1. And from those, I can solve those 2 equations to define the heights here and here, and then linearly interpolate to get everything else. The nice thing is that I can reformulate this a little bit by plugging and chugging right here, and I get a nice little plug and chug expression for shear and moment or for shear influence lines. Don't worry, I've got this summarized on a later slide. Okay, does that make sense? Everybody okay with that? Okay, all right. Moment influence lines, it's the same idea, okay? For moment influence lines, what I do is I release from the structure the ability to resist moment at the point of interest. So, as you said, we're going to put a moment release right here or a hinge, okay? Now, what I'm going to do for moment releases, though, is I'm going to take this point and I'm going to put it through a unit rotation, okay? So, the way I'm going to do that is I'm going to take this point and I'm going to lift it up. And I'm going to lift it up a specific magical amount. And you're like, how much is that magical amount? Okay, so let's say here's my beam. I'm going to take that beam, I'm going to put a hinge right here, and I'm going to lift it up like that. Okay, and I'm going to lift it up some magical amount, h. Okay, now how much am I lifting it up? What is h? Well, I'm lifting it up such that I achieve a unit rotation. Okay, remember when we were talking about deflections and we said that rotations and slopes were interchangeable, that those terms kind of meant the same thing? Y'all remember that? So what is the slope of these 2 lines? What is the slope of that line? It's h over L1. What is the slope of this line? It's h over L2. So what I can do is I can say, all right, I need to move it through a unit rotation, so the sum of those slopes has to equal 1. The total slope has to equal 1. And what is the slope? H over L1 plus H over L2. So I can solve for those slopes pretty easily, okay? Or that height pretty easily. And don't worry, if this seems a little scary, when we actually start doing some problems, it's a lot easier than you would think, okay? Anybody have any questions on this? Okay, so here's my summary. And like I said, I was going to have a nice, pretty summary slide for you. So for shear influence lines, I think this entire semester, I mean, we haven't really had a class this semester where there's like formulas you need to memorize, right? It hasn't really been that way with this class. But maybe this is a formula you want to memorize for shear influence lines and moment influence lines. So this is my expression I can use to solve for heights for shear influence lines. This is my expression I can use to solve for the heights on moment influence lines. Now, a couple things about shear and moment influence lines that are worth mentioning. Actually, I'll do this slowly. So a couple things worth mentioning. Number one, whenever you're drawing influence lines for internal shears and moments, they will always equal 0 at the supports, okay? And the reason for that is, so if I have, let's say I have a beam right here. And let's make it an interesting beam. Let's put, support here, support here, support here, and let's put a hinge right here, okay? And let's say my point of interest is right there. That's my point of interest. If I put a load right here, let's put a 1 kip load right there. What is the internal response inside the beam if the load is directly over the support? It's 0, right? Because all the load is going directly to the support. If here's this table, and I'm sitting right on the table leg, the table isn't seeing anything, right? It's just going directly to the support. So whenever you draw either a shear influence line or a moment influence line, here the value is 0. Here the value is 0. Here the value is 0. Here the value is 0, okay? At the supports. Again, for determinate structures, influence lines are lines, okay? They are lines, okay? And third, just like last time, if you ever have an internal hinge, they will change the direction of the shear or moment influence line. Sound good? So what we're going to do is we're going to go back to those same 2 problems that we did last time, and now we're going to draw influence lines for the shears and moments, okay? So let's go back to those problems. Okay, so let's do influence line for example 1 first, okay? So put my little marker on here. Okay, so here's my influence line, and I just want to recap what we did last time. So last time, all we did is we used basic geometry to kick out one of these supports, and then it was just a straight line. So we used slope ratios to figure out, well, if that's 1, then this is 1/3, and that's -1/3, and if that's 2/3, that's 4/3. We just use basic linear interpolation. We also did some statics to say, okay, let's actually put the load here and see if we get the reactions that the influence line yields, and by golly gosh gee, we did, okay? So now we're going to do something similar. So it's the same beam. So again, I kind of cheated here because I put the same image here on the screen. I don't want to have to draw that out again. And I know I stretched it. It looks kind of stretchy. All right, so, oh, I need to put my pen on. There we go. Okay. So now what we're going to do is we're going to draw the influence line for shear and the influence line for moment. So let's do shear first. And we're going to draw the influence line for the shear at B. So on this problem, our point of interest is being defined by the letter point B. On the next problem, it'll be defined by a given section. Okay? So before we start drawing, are there any values that we can identify right now that we know are going to be the values on the influence line before we even draw anything?
L1 and L2.
Well, L1 and L2, okay, that's true. So we know that L1 is 20 feet and L2 is 10 feet. But I'm talking about magnitudes on the influence line. What is the magnitude of the influence line going to be right here? Well, we don't know what's going on here, but what about right here? 0. So the influence line better be 0 right here, and it better be 0 right there. So we'll put that as 0. So before we even draw anything, okay? And does everybody understand why the influence line better be 0 right there? Okay, because if you put the load right there at C, the beam doesn't see anything. Okay. Now, what we're going to do, okay, so let's follow along. So what we're going to do here is we're going to install a shear release right there at point B. So see how I installed that shear release? Okay. So we are going to deform point B such that we have a total displacement of 1. Now the left side, does the left side move up or does the left side move down? Down, right? Left side moves down, right side moves up. Okay? And again, that just comes from the fact that if I have a beam and I cut it and I separate it, this is positive shears. Left side goes down, right side goes up. Okay? So what I'm going to do is, all right, let me ask you a question before I start drawing anything. If I put this release here, how many different rigid links do I have in the beam now? Originally it was just one solid piece. Now I've got 2. So I'm going to have 2 line segments. And I propose what it's going to look like is this. I'm going to have one side that goes like that, and another that's going to go like this. Now, let's just sort of draw this and let's digest it. Okay? So let's see what I did here. So let's do this. Okay, so let's do the shear at B first. Okay, so what I have here, so I've got this. I've got that. So if this side goes up on the right, keep in mind it's going to pivot around that. It's going to seesaw around that. And if this side goes down, it's pivoting down. Do y'all see why it's doing that? Y'all see that? So that left side is just sort of pivoting around that roller. Okay? So I've got this as my influence line. But I don't really have any values. I got to figure that out. Okay? So let's see if we can figure this out. Okay? So what I'm going to do is I'm going to call this dimension here H1, and I'm going to call this dimension here H2. Okay? And as Mr. Dangerfield said, this L1, this is 20 feet, this is 10 feet. Make sense? Now, the way that we're going to figure this out is we're going to say, okay, H1 is to 20 as H2 is to 10. Now, I gave you a plug and chug expression. If you want to memorize that, that's great. I'm going to be honest, I don't know that I use it all that much because I kind of just, look at the ratios. And so let me show you how I do it. All right. What I'm going to do is I'm going to say that I'm going to do that. Is that right? Take the 10, multiply it by both sides. I get H2 is 10 over 20 H1 or H1 over 2. Is that fair? So I would agree that, or I would claim that this height is half of this one. Are you all okay with that? So if that's the case, what I'm going to do is instead of H2, I'm going to substitute H1 over 2. So what is 1 plus a half? What's that? 1.5 or 3 halves. So therefore, H1 is 2/3. And H2 is going to be 1/3. What do you think? So here's what I propose. I propose that this is 2/3. I'm going to call it negative since it's going down. And this is positive 1/3. Now, if you want, you can use the plug and chug expression. You can say, you know, H1 over L1 equals 1 minus H1 over L2. If you want to do it like that, you can, and just plug and chug and solve. But I kind of just like to look at it and use a bit of logic. That's kind of how I do it. All right, let me take a step back and see if anybody has any questions. All right, have I fully gotten all the values on the influence line, or have I missed one? I missed this one. What is that, by the way? Negative 1/3. It's just a line, right? This is 10 feet, this is 10 feet. So if you go up 1/3 in 10 feet, you're going to go down 1/3 in 10 feet. That's just negative 1/3. Boom. Influence line, done. Pretty easy, right? Okay. Let's do the next one. All right. Now the next one, I'm going to cheat a little bit. Because I want to have a beam image that's like readily referenceable. Okay. Bless you. So I want to have a beam image that's readily referenceable. So I'm going to put that right there. And we're going to draw the influence line for the moment at B. So before I start drawing, any two values that I can easily identify? There we go. 0 right here. 0 right there. I'm actually going to be a little precognitive and put that there because I think that's going to get in the way. Okay. All right. So we're going to draw the influence line for B. So we're going to remove from the structure the ability to resist the moment at B. So what that means is that I'm going to install a hinge. So I'm putting a hinge right there at point B. Okay. So if you're wondering about my symbol there, it's just sort of like that, like a hinge. So it's like a little hinge right there. Okay. And then I'm going to move it through a unit rotation. Okay. So according to my positive sign convention, which goes like that and like that, I'm going to rotate this side up and that side up. So what's going to happen is it's going to peak up. So if it's pinned down right here, okay, that means that this side is going to go like that. Okay. Now, I want everybody to watch this up here. Is that right? You see what I did? That's wrong, isn't it? This is an influence line that I have seen on exams so many times. It's just always up and down. No, it's got to go through 0 here, right? What's happening is this, okay? What's happening is here's the beam, right? Here's the beam. Support, support. I put a hinge right here. When I rotate this side up, it's pinned, so it's got to pivot around that support. So it's going down like that. That, ladies and gentlemen, is the influence line for the reaction at B. Okay. Right, because what's happening here, I'll put this on here as well. So if I install a hinge right there, do that, this side is going to pivot around that, and that side's just going to go up. Okay. Now, I don't have any values, so I need to figure this out, okay? So the way that I'm going to do that is I've got this line right here, which I'm going to call slope 1, and this line right here, bless you, which I'm going to call slope 2, okay? And how do I quantify the slope of those lines? And let's be clear, we're going to call this dimension right here, we're going to call this H. See, I propose that slope 1 plus slope 2 has got to equal 1, a unit rotation. What is the slope of line 1? Rise over run, right? So H over what?
20.
Well, what about this one? H over 10, right? So H over 20, bless you. Right? H over 10 plus H over 20 is 1. Now this starts to go back to Math 127. So what we'll do is we'll say, you can do this however you want, 10H over 200 plus 20H over 200 equals 1. (20/3). Did I do that too fast? That pretty easy? So I just multiplied, to get them into a common denominator, I said, well, 20 times 10 is 200, so just multiply that times 10, multiply that times 20, however you want to do it. This is positive 20/3, 6.67. So by the way, what is this? Negative 20/3. Okay. All right. Before I move on to the next problem, I want to make sure we're clear on any questions, and I want to talk about how we might use them later. Okay? All right. But let's be clear. Does anybody have any questions on this? Okay, good stuff. All right. I do want to make a very, very light observation. I'll do it inside here. Let's do the shear first. And we'll do a moment one as well. Okay. All right. I'm going to go to the influence line. Let's do the shear one first. And I'm going to put some symbols here. I'm going to put negative, positive, negative. Okay. So what this is telling me, let's be clear. Okay, what this is telling me is that if I'm looking at point B, so remember, The influence line tells me the shear at point B as a unit load moves across the structure. And I get negative, positive, negative. So what this is telling me is that as I move that load across the structure, I get changes in sign, right? Sometimes I get a negative shear, sometimes I get a positive shear. With me on that? Okay. So how do I use that? How do I use that from a design standpoint? Okay? Well, I want you all to consider that you have a beam and you're designing it for a distributed load, but a distributed load that can move. So think about this. Think about that this is a bridge. Let's say this is a bridge, and I've got this distributed load. And let's say that distributed load is representing traffic on the bridge. And so the traffic could be in all sorts of different patterns. I could have traffic everywhere. I could have a little bit of traffic right here, a little bit of traffic right here, a bunch of traffic over here. I could have the traffic in as many different permutations as I would like, right? There's nothing that says the cars just have to be here. They can be anywhere, right? So the question is, where do I put that load to generate the worst case shears? And I propose that what you do is this. So what I'm going to do is I'm going to call this Vmax positive, Vmax negative. And we're going to talk about this a little bit on Friday and Monday, but I just wanted to put this thought out there. I propose that for the worst case positive shear, I should just put that load right there. Why there? Why nowhere else? Because it's the only place on the influence line that gave me positive shears. So if I want the worst case positive shear due to this load, put it there and nowhere else. So if that's the worst case positive shear, how do you think I'm going to get the worst case negative shear? Maybe everywhere else. Maybe this. And then I propose that for that distributed load, I could calculate a Vmax positive and a Vmax negative. And I can say that for that distributed load, that is the extreme ranges of shears that you could expect. Does that make sense? That extreme range, we call that an envelope. Okay? So when you hear me use the term envelope, that's what I'm talking about. Okay? So for moments, maybe what I'll do is I'll say, okay, let's say everybody's paying attention this morning. Where do you think I should put this distributed load to generate the worst case positive moments? Somebody tell me. The worst case positive moments.
Everything led through the roller support.
Everything between here and here, right? So I'll put that load here. What about Mmax negative? Everything on the overhang. And so what I can tell you for that point is that is the worst case response you can expect at that point. And so what do we do as bridge engineers? We just do it again and do it again and do it again for every 10th point along the span. And that's what we design our bridges for. That's basically it in a nutshell. Does that make sense? That's what we call an envelope. I just wanted to plant that seed in your head because we're going to do that later. Okay? So far, so good? All right. Can I move on to the next one? let's move on to the next one. The next one, we're just going to draw the influence lines. We're not going to get fancy with the applications yet. All right, this is our next one. We're drawing influence lines for the internal shear and moment right there. So right here, next to the point C, the section 1-1. So we've got two influence lines to draw. All right, I'm going to lean on your help a little bit on this one. I'm going to see what you all can come up with. So we're going to go down. Okay, let's do this one. So we're going to draw the influence line for the shear at this section. Before we draw anything, any values you can tell me right offhand? 0 at A, B, and C. Before you do a thing, I want a 0 there, 0 there, 0 there. So, what we're going to be doing for shear, installing a shear release. This side goes up, this side goes down. How many rigid links is this going to split the beam up into when this is all said and done? 3. So 3 links means there's 3 different line segments. 3 of them. Okay? So I'll start. I know that we're going to go up, something about like that. All right? Down here, we're going to go down. So it's going to go like this. What happens right here? It goes back down. The hinge changes directions. Make sense? Okay. So let's start identifying some points of interest. So this dimension is H1. This is H2. This is L2. What's L1? 14 feet, right? So I'm curious, are you all able to do this one on your own? Tell me what H1 and H2 are. So we've got, well, that's bad. I can do better than that. H1 and H2 are 6, or H1 over 14 is equal to H2 over 6, and H1 plus H2 is 1. Can anybody tell me what they, you tell me. I'm going to make you do a little bit of work this morning. What do you got for H1 and H2? Uh-oh, I'm making you break out the Casio FX115 ES Plus or similar scientific calculator Monday morning. I know, I'm horrible. I want to see what you all come up with. Anybody have an answer? You got your hand raised. What you got? Oh, you're still working on it. let's see what we can do here. So H1, let's do it like this. Let's do it like this. So H2,
Would H1 be 0.7?
there you go. H2 is 6 over 14 H1, so therefore H1 plus 6 over 14 H1 is 1. So this is 14 over 14 H1 plus 6 over 14 H1 is 1. So 20 over 14 H1 is 1. So this is 7/10, which makes H2 3/10. Does that make sense? So we're going to need a little bit more room down here. Okay, so that makes this negative 7 over 10. That makes that positive 3 over 10. Now, here's the kicker. How are we going to get that?
It's 4/10.
How did you get that? You know it's right, but how? The slope of the line, right? So how about this? How about 7/10 is to 14 as something, we'll call it H3. If you want to have a new term here, we'll call this H3. As H3 is to 8. Therefore, H3 is 7/10 8 over 14, which is, so let's see, that right there is 2. And then, so that is 8 over 20 or 4 over 10. What do you think? Not too bad, right? Okay. All right. Like I said, apologies, I'm going to cheat. I want to be able to see what's going on here. Got to put the pen on. All right. Oh, I can do better than that. Let's do it. So, again, 0, 0, 0. All right. We install a hinge. Rotate that side like that side like that. And again, how many rigid links do we have now in the beam? 3, because we have 1, 2, 3, and this central one pivots around B. So we get this side goes up, this side goes like that, pivoting around B. And then like that. And then how do we get that height right there? How do we get this height? How do we get that? So we say that H over 14 plus H over 6 is 1. So 14 times 6 is what, 84? So 4.2. And then we'll call this height right here, and I know we're getting short on time. We'll call this height H hinge. So we'll say that H, so we'll say what? 4.2 over, we'll say 14 is whatever this hinge height is over 8. So therefore, the height of the hinge is 4.2 times 8 over 14. And I think that comes out to 2.4. So that makes this negative 2.4. Okay. Any questions? All right. So here's what we're going to do next time. So, you know, ironically, I've covered just about the grand majority of everything with influence lines except for two things. We need to deal with fixed supports, and I do need to show you a little bit about how to draw an influence line for a truss. Okay. Friday and Monday, we're going to start doing applications. So with that, that's all I got, everybody. I will see you all on Wednesday.